Swayam Prabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems for CSIR-NET. In the module 10, we will be looking at organic reaction mechanisms involving substitution reactions with electrophilic, nucleophilic or radical species. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. So in this particular session, we will be looking at various organic reaction mechanisms involving substitution reactions with electrophilic, nucleophilic or radical species. Let us look at the first problem. So this problem appeared in December 2019. So identify the product formed in the following reaction. A starting material is given. So we have a iodo derivative, a nitroiodo derivative with a good leaving group, that is OTS. And this is treated with PHSNA and DMF as a solvent, and we have to find out what is the product formed in this particular reaction. So we have four different products given as an option A, B, C, D. In the first one, we have the OTS is replaced by SPH group, and in the second one also the OTS group is replaced by SPH. The difference between the first one and the second option is only the change in the stereochemistry of the product that is formed. And in the third one, the iodo group is replaced by the SPH group, and in the fourth one, the nitro group is replaced by the SPH. So these are all the four different types of product that may be formed in this particular reaction. These are given as the option. We have to find out what is the actual product that will be formed. So let us look at how the reaction will proceed. This reaction is basically a SN2 reaction. So here we have a nucleophile, that is the PHS is the nucleophile that will be involved in this particular reaction. So this is Na plus and PHS minus. So thiolate anion. So the thiolate anion can easily attack the carbon atom, that is the benzylic carbon is the one that is being attacked by the thiolate anion. So as this reaction is a SN2 attack, that means inversion of the stereochemistry that will happen. So in other words, if it is pointing above, then the product is going to be formed as a pointing below. So that is what is actually going to happen. So when we look at that, the stereochemistry is inversion at the reaction center. So the final product formed will be this one, because the thiolate anion cannot displace the aromatic or the nuclear substituted groups. So in other words, the iodine cannot be replaced. Similarly, the nitro group can also be cannot be replaced by the thiolate anion. Let us move on to the next problem. So this problem appeared in December 2011. So here the major product formed in the following reaction, a chloroanisole derivative is given. This is treated with sodamide in the presence of liquid ammonia. We have four different products that will be formed. We can say this as A, B, C and D. So in the first one, the chlorine is replaced and the methoxy is also replaced. In the second one, only the chlorine is replaced by the amide unit, and in the third one, both that OMe group and the chloro group is replaced with amino NH2 group, but the positions are different. And in the fourth one, both the OMe and the chloro are replaced but by the NH2 group. So these are all the four different type of product that will be formed as given in the options A and B and C and D. So we have to find it out what is the correct product that will be formed in this reaction. So this reaction basically follows a arraign mechanism. So this is basically the elimination addition mechanism in this particular case. The base, that is the NH2 minus, that amide anion abstracts the orthoproton to the halogen unit. So when this hydrogen atom is replaced, we end up with the concomitant removal of the chloride anion also, that leads to the formation of the benzene or the arraign type intermediate. So this arraign intermediate can be attacked by the NH2 unit, that is the NH2 minus anion, either on this carbon or on this carbon. So we have two options that are possible. So if it attacks ortho to the methoxy unit, we end up with this particular product. If it attacks the meta carbon with respect to the anisole or the methoxy ether, we end up with this product, that is the meta derivative. So there are two possibilities that can happen or occur in this particular reaction. So here we have to find out what is the major product. Of course, both the products will be formed in this particular case, but the orthoisomer will be formed at around 40% and the meta-isomer will be formed in 60% yield. So in other words, what we can say is the meta-isomer is the major product that will be formed in this reaction. Of course, the ortho product will also be formed in this reaction. So we have both the product ortho and the meta product that will be formed in this reaction. So this reaction proceeds via the arine intermediate. So this is happening through the elimination addition mechanism. In the first step, the elimination takes place, the elimination of the Cl minus takes place, and in the second step, addition of the second nucleophile, that is the NH2 minus, takes place. So this is the overall mechanism for this reaction, and this reaction is basically called as the sign substitution. So what is a sign substitution? In the sign substitution, one nucleophilic unit in the aromatic ring is replaced by another nucleophilic unit, but the incoming nucleophilic unit occupies a place which is different from the place where the nucleophile already left. So here chlorine leaves from a place which is ortho to the methoxy unit, and the second incoming nucleophile attaches itself to the meta position as the major product. So here what we say is we also have the same place where the chlorine is replaced by the nucleophile, that also occurs, but since the majority of the product formed is the sign substitute adjacent to the chlorine group, so we call this as a sign substitution. Or so let us move on to the next problem. So this problem appeared in June 2011. So the major product formed in this following reaction is, here an epoxide is given, and similar to the first case what we have seen, we have a thiolate anion. So basically the thiolate anion opens up this epoxide ring. So we have various combination of the product that will be formed, A, B, C and D. So in the product A, the epoxide oxygen retains its stereochemistry. So this is above the plane, and that is also retained in the final product. The incoming nucleophile comes and attacks from the bottom side, or attaches itself from the bottom side. So that is one type of product. In the other case, the position of the attack is different. In the first case, the nucleophile attacks from this particular carbon. In the second one, the nucleophile attacks from the bottom, the next carbon. So we have two different type of product that will be formed. In the other two cases, the attack is either from the opposite side, from the two different carbon atoms. So that is how we have four different type of product that may be formed. We have to find out which reaction actually occurs. So here again, as in the previous case, it is a SN2 attack. So that means it is a rear side attack of this epoxide. So when the thiolate anion attacks, it will attack from the less hindered side. If you look at this particular structure, we have a methyl group that is present here. So this methyl group actually flanks, or it makes this area little bit crowded. So that is the reason the thiolate anion does not attack from the top side, and it attacks only from this side of the epoxide ring. And here again, the attack actually takes place from the bottom side, that is the opposite side where the epoxide is actually present. So that is the reason when the epoxide opens up, the hydroxy unit remains in the same stereochemistry. That means it is above the plane, remains above the plane all the time, and the nucleophile attacks from the bottom side. So this is given as the dashed lines. So that is how we can say this particular reaction occurs with the inversion of stereochemistry, and the attack takes place from the less hindered site. So let us move on to the next problem. This problem appeared in December 2014. So here the product B in the following reaction sequences. So the reactions are given. We have a cyclopentadiene as the starting material. This is treated with the 1 equivalent of bromine in the presence of hexane at room temperature. So that is step 1. That leads to some intermediate A, and this intermediate is treated with excess of dimethylamine. That leads to the final product B. So we have to now identify from the 4 combinations that are given here what is going to be the major product in this particular reaction, whether it is A, B, C or D. So in both the cases, in A and B, the only difference is the stereochemistry is anti in this particular case. Here it is cis or syn, and the addition takes place on 2 different carbon atoms which are away from each other. They are separated by in between 1 carbon atom. And the product C and D, in C we have a anti-addition because one is above the plane, another one is below the plane, and in D both are in the same side, or it is syn or cis addition. So these are all the 4 combinations that are happening. So if we look at the reaction very carefully, the bromine addition happens first. So we have a alkene bond, we have a bromine addition. So we do need to know how the reaction actually takes place, because bromination reactions are basically in this particular case happens by the bromonium ion attack as the first step, and the second step is the attack by the bromide ion. So the first step is bromonium ion attack, second step is the bromide anion attack. And because the bromine is basically a bulky group, so our expected mechanism is a cyclic bromonium ion will be formed, and always when the bromide ion attacks, it attacks from the opposite side where the bromine is present. In other words, what we can say is the bromine addition to an alkene double bond is always anti-addition. So this is the only thing we have to remember. And in the second step, we are going to attack or replace the bromine with the another nucleophile. So whenever this kind of reaction occurs, what we can observe is basically that is going to be like a SN2 attack. When it is an SN2 attack, so that means the stereochemistry of the starting material will be completely reversed in the final product. So these are all the 2 things we have to remember before solving this problem. So now if we look at how the reaction actually proceeds, so let us look at one of the double bond that is brominated. So we end up with the anti-addition, because as we have discussed now, the bromine addition always takes place as an anti-addition, because this intermediate that is involved is bromonium ion, and the bromonium ion is basically the cyclic bromonium ion. So that cyclic bromonium ion, when it is formed, that will be opened up in the second step by the bromide ion attack. So we have a bond here, we have bromine here, and this will be having a positive charge. So when we draw the structure, so the second bromide ion can attack from any one of the carbon. So it has to attack only from the opposite side. So that is how we say. And when it attacks from the opposite side, we end up with the anti-product, or the trans product will be formed. And here if you look at the stereochemistry, one of the bromine is above the plane and another one is below the plane. And the next step is the SN2 attack by the dimethylamine. So when the dimethylamine attacks this one, so what we end up is the stereochemistry of the top carbon is replaced, is changed to the other side. Similarly, the bottom carbon stereochemistry is inverted. So this is how the reaction actually proceeds. And what we can say is the last step is the inversion of stereochemistry takes place. So the overall product that will be formed is the 2 substituted groups will be present ortho to or adjacent to each other. So let us move on to the next problem. So this problem appeared in December 2016. So here the major product formed in the dinitration of 4-bromotoluene is. So the 4-bromotoluene is nitrated but not mononitration, it is a dinitration. So we have to find out what is going to be the product. So we have 4 products, A, B, C and D. So in the A we have 2 nitro groups that are present meta to each other. In the product B we have 2 nitro groups which are present ortho to each other, and in product C we have 2 nitro groups that are present meta to each other, and in the 4th one we have 2 nitro group that is present para to each other. So here there are various things we have to remember. One is we have in the bromotoluene we have bromine and we have methyl group and we have a bromine atom. So there are 2 groups which are already present, and they both exert a different type of effect on the aromatic system. So the incoming electrophile, because when we talk about nitration, the nitration occurs by the nitronium ion addition. So that means the the aromatic system should be electron rich in nature for the nitronium ion to attack. So this is one thing we have to remember. So which carbon is going to be electron rich will decide how the nitronium ion will attack. So this is the first step. So once the nitro group is introduced, what will happen is the system becomes deactivated because of the presence of the first nitro group. So we have to look now, if the second nitration has to take place, so what is going to be the carbon which is still going to be electron rich where the nitronium ion can attack. So these are all the 2 things we have to identify. Once we identify these 2 things, then it becomes easy for us to predict what is going to be the product. So let us look at how the reaction will actually proceed. So we have, as I mentioned, we have 2 effects that we have to look at. One is the methyl group's effect, the second one is the bromo group effect. So we have a methyl group which is having a plus I effect. So this is basically electron donating in nature. So whenever we say plus I effect group is present, that will basically activate the aromatic system, especially the ortho and para positions are activated by the plus I effect group. And the second one is we have a bromo unit that is present. The bromine has actually a negative I effect, so that means it will deactivate those positions. So comparatively, methyl is more powerful than bromine in this particular case. So in other words, what we can say is the ortho positions are going to be more electron rich because these are going to be activated by the presence of the methyl group. So the first nitration actually takes place on this particular carbon. So the ortho nitration takes place very effectively. But then what is going to be the second one? So here the most challenging thing for us to understand is whenever there is a nitro group is present, what the nitro group will do is this will actually deactivate the aromatic ring. So in other words, the electron density at certain places becomes less compared to the other, because depletion of electron density is more pronounced than increase of electron density. So when a nitro group is present, we always look for the carbon which is less affected compared to the more affected carbon. So that way if we can easily identify which place will be more affected, because when it affects, what happens is nitro group is electron withdrawing in nature. So whichever carbon that is affected will become electron deficient. So when it is electron deficient, it cannot be attacked by the nitronium ion in the second step, because this is actually electron seeking group. And if a carbon is electron deficient, then obviously we can say those carbon cannot be attacked by the electrophilic nitronium ion. So this nitro group now deactivates some of the atoms. So that is the reason we say the meta positions are deactivated more. So when we have a meta directing group, the nitro group that is present, meta to a ortho para directing group. So these are all little bit complicated things what we are going to talk about. We have a ortho para directing group, methyl group that is present, and when the meta directing nitro group is present meta to the ortho para directing group, bromine is also orthopara directing in nature. So when the first nitro group is present, this is basically present meta to this particular orthopara directing group. So in that particular case, then the electrophile, incoming electrophile goes ortho position with respect to the nitro group. So here we can say both the methyl and the bromine, both are orthopara directing groups. So that's the reason we can say what is going to be the place where the nitro group will come. The nitro group, one place activated is this carbon, because already there is a methyl group, so this carbon cannot take any further nitration cannot happen on this particular carbon. So that is the only ortho position with respect to the existing nitro group is this carbon. So that is the reason the second incoming nitro group comes and attacks only at this particular position. So this is how we can say the second nitro group actually directs the incoming nitro group to ortho position with respect to the place where it is actually present. Of course, there is also another possibility. The incoming nitro group can also go to the para position, but para position is not highly possible in this particular case. That's the reason ortho substitution takes place very effectively. So the final product is going to be formed as shown here. So the both nitro groups are adjacent or ortho to each other in this particular product. Of course, Hammett and Illingworth rule is generally used for explaining these kind of reactions. So let us move on to the next problem. So this appeared in December 2019. So the major product formed in the following reaction. So we have a lactone that is present here, and one of the nitrogen is protected as a phthalimide group in this particular case. And the first step is reaction with HBr, second step is reaction with methanol under acidic conditions, third step is reaction with the MEPOET, that is phosphonate compound, and the last step is the hydrolysis under acidic conditions. So these are all the four different reactions that are being performed on this particular lactone. So we end up with the four different product as shown here as an options for this particular reaction. So the first product A, B, C and D. Between all the four products, the first product does not have any group containing the phosphorus unit, so this can be ruled out. The other three are only having the phosphoric acid group that is present here. So any one of them could be our expected product. So let us look at the mechanism, and then we will find it out how the reaction actually proceeds. So the first step is basically the attack of the bromide anion, because this reaction happens in the presence of HBr. So the bromide ion attack is the first step that is happening. This is the electrophilic carbon. So the electrophilic carbon is attacked by the bromide anion with the negative oxygen pulling out the pi bond at the electron to become a negatively charged anion, and we end up with the tetrahedral intermediate as shown here. So this is the first step that is happening, and once the tetrahedral intermediate is formed, since there is a negative charge on the oxygen atom, charge reversal takes place as the second one. So when the charge reversal takes place, this actually opens up the lactone ring, and we end up with the acyl bromide with the oxide anion. So this is how the ring actually opens up by the attack of the bromide anion. So once the attack takes place, what is going to be the next step is basically the second step is during this process itself the reaction actually undergoes hydrolysis, because the acyl bromides are quite unstable. So under the reaction conditions, because HBr HBr reaction is carried out under acidic aqueous conditions, so the bromide ion gets hydrolyzed very quickly to the carboxylic acid, and this oxide anion also becomes a hydroxy derivative. So we end up with the hydroxy acid as shown here. So what is the next step? The next step is treatment with methanol in the presence of acidic conditions. So the carboxylic acid is getting converted to the corresponding ester unit. So this is what the reaction, the second step of this reaction is reaction with the methanol in the presence of acidic conditions, that leads to the corresponding ester. The hydroxy ester is formed. So once the hydroxy ester is formed, what is the next step? So the next step is the reaction with methyl phosphonate reaction. So when the methyl phosphonate reaction occurs, this hydroxy group is lost, and here the phosphorus unit is attached to this particular substrate, and we end up with the phosphonic acid as shown here. So once the phosphonic acid is formed, what is going to be the next step? This is undergoing the last step, that is the hydrolysis under acidic condition. So when the hydrolysis happens, what happens is, in this particular case, the phthalimide unit is actually hydrolyzed under acidic conditions. So what we end up is basically this is the protection that is used for the amino group protection. So the amino group is liberated during the phthalimide deprotection happens under acidic conditions. So we end up with the amino group. So when we have the amino group, this ester also undergoes hydrolysis under this particular acidic conditions. So what we end up with is basically the corresponding amino acid is formed with the phosphonic acid unit that is present here. So this is the overall reaction that is happening in this particular case. Let us move on to the next problem. So this problem appeared in June 2014. So only two products are obtained in the following reaction sequence. The structure of the product from the list 1 and 4 are, here we have 4 different combinations. This is a alpha beta unsaturated carbonyl compound. This is treated with sodamide, and dibromoethane is also 1,2-dibromoethane is also used in the one of the steps. So we are supposed to get 4 different products that are shown here. The first and second products are basically a cyclopropyl derivative with the carbonyl unit, and third and 4 are alkenic compounds with the carbonyl unit. So these are all the 2 different combinations that are possible, and the product that will be formed may be 1 and 2, or 2 and 4, 1 and 3, and 3 and 4. So these are all the various permutation combinations are possible. So we have to identify how the reaction actually proceeds and what are the 2 products that can exist as a final product in this particular reaction. So let us look at how the reaction actually proceeds. So we have a amide anion that is involved in this reaction. So the amide anion abstracts one of the methyl proton from this particular carbon atom. So that leads to the anion formation. So this is a very simple step which you are already familiar with. So once the anion is formed, what is going to be the next step? The next step is reaction with the 1,2-dibromoethane. So when the 1,2-dibromoethane is added, the shift of double bond, the negative charge happens, and this alkyl unit, actually this alkenic carbon attacks this particular 1,2-dibromoethane with the concomitant loss of the bromide anion. So this is nothing but the SN2 attack of this particular negative charge. Now you will be wondering whether this anion directly attacks or this alkenic bond that attacks. So as in organic chemistry, we always say there is various reactions which will be occurring simultaneously, and many of these reactions are basically considered as microscopic reversible reactions. In other words, all these reactions are occurring in equilibrium with each step. So the thermodynamically stable product will be formed in most of the cases after certain time. But in the beginning stage, both the products or both the probabilities exist in those kind of reactions. So that is the reason many times organic reactions give comparatively less yield, simply because there are various competitive reactions that are occurring, and the stability or the thermodynamic stability of the formed intermediate decides which path will be more happening. That is what we can say. So in other words, what we can say is this carbanion directly attacking this particular 1,2-dibromoethane is also possible. The second, the carbanion's negative charge can be shifted towards between the carbon and carbon bond, and this alkenic carbon can also attack this 1,2-dibromoethane. So both are possible, and according to the stability, what we can say is this alkenic carbon attacking this particular 1,2-dibromethane is the most favorable one. So then that leads to the condensation of or addition of this particular unit to the alpha carbon of the carbonyl compound. So we end up with the exocyclic double bond in this particular case. So once this happens, what is going to be the next step? So in the next step, we still have the amide anion that is present in the system. So this amide anion abstracts the most acidic proton. So we have two different type of acidic proton that is present. One is the methane proton present here at the substituted carbon. Another one is a methylene proton that is present alpha to the carbonyl compound. So this proton is more acidic compared to this hydrogen atom. So that is the reason the amide anion abstract this proton, leading to the carbanion on this particular carbon. So once a carbanion is formed in this particular carbon, what it can do is this carbanion can attack this particular carbon by a SN2 type attack. So this leads to the formation of a cyclopropyl derivative, and this internal attack of the carbanion is a crucial step for the formation of the cyclopropyl unit. So once the cyclopropyl unit is formed, then this is one of the product that is we are expecting, and this can undergo a resonance with another compound. So that is what is shown here. So one of the hydrogen which is shifted from here, where the alkenic bond becomes a methyl unit. So that is how we end up with the alkene from the exocyclic double bond is shifted to the ring system. So these are in resonance to each other. So that's the reason what we can say in this particular reaction. These are all the two products that will be formed in this particular reaction. We only have the cyclopropyl unit. This is again a bicyclic system, but these two are in spiro ring system. So here we have the spirocarbon that is present here. So this spiro ring system formed, not the other one. So that is how we can say in this particular case, these two are the resonant stabilized compounds that will be formed.